Hello and welcome. I'd like to start by thanking Iowa State, the IMSE department, and Danfoss for their support and cooperation throughout our project. This semester, our group worked with Danfoss to improve operations on one of their manufacturing lines, which produce hydraulic pump housings. We were provided with data on the tool tip position and load for over a week. Our task was to use this data to better inform plant managers and allow Danfoss to create more optimized maintenance schedules, leading to less unplanned downtime and fewer scrap parts and tools. With this in mind, our project objective began to take shape: help improve maintenance operations and reduce downtime for the production line.
Understanding the data provided to our team. We received 6 days of data for each of the 4 Mazak machines, totaling 2.3 million rows of data. From this data, we are primarily interested in job numbers, which are very similar but more specific than part numbers, X, Y, and Z load. For data preprocessing and analysis, we used Python with the matplotlib and pandas packages, as well as Excel. We removed data unrelated to X, Y, or Z load, pivoted our 3 variables of interest from rows to columns, and created data frames for each unique combination of machine, job, and load type. Here we have our 4 Mazak machines, then narrowed down to 1, broken out by the 2 most frequently ran jobs. Job 2931 accounts for 39% of our data, while job 2934 accounts for 18% of our data. And by each machine and each job, we have broken out each component of load. Cycle identification within the data. We created a column to track time elapsed from each cycle start callout by the machine. This enabled us to plot several cycles against change in time, which you can see here on the right. Cycle identification is required for us to create control charts with end cycles.
Control charts are a tool primarily used to monitor process stability and identify special cause variation. Control charts were produced for each Mazak machine, both of the high-frequency job types, and for each X, Y, and Z load variable. These methods will provide Danfoss with a baseline indicator of their CNC machining process stability and help them monitor this process over time. This first example showcases an in-control process. As you can see from this second example, when keeping the machine number and variable the same while changing the job type, the control chart flagged a point that was out of the upper control limit, indicating that the process is out of control. Danfoss can use this information gathered from the control charts to further investigate the root cause of their issue. Additionally, a method known as the Rainflow Counting algorithm was used to further investigate the tool fatigue of the CNC machines. The below rainflow plots show where high tool damage events occur. The three-dimensional plot shows the number of instances where these events happen. Danfoss will be able to use this information to identify and monitor events that further fatigue their tools, which can ultimately lead to more accurate maintenance schedules and far less unplanned downtime.
The economic impact for the project will be calculated by a cell, which is assumed to be the entire Mazak area, including all 4 machines. The numbers used to estimate the economic impact were provided by Danfoss. Unplanned downtime year to date is 180 hours. Hourly loss of production is $450 per hour. Hourly run rate by cell is $100 per hour. By providing Danfoss with the rainflow diagrams, control charts, and the code for continuous analysis, we have estimated that our project could reduce downtime by 50%. With our deliverables, it is assumed that our project would save Danfoss $55,500 for the cell area per year. Thank you, Danfoss, for allowing our team to work with you, and thank you for your time.